Good day, students. Myself, Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. I welcome you all in the enlightening session of MSc Previous Physics lecture series. In our lecture series, we were discussing, I am dealing with the paper first, that is classical mechanics. And in this paper, we were discussing the central force problem. Today we will discuss the Kepler laws and we will deal with the Kepler first law. So we are going to start with the discussion of motion under inverse square force. For this purpose we are taking our force to vary as inverse of square of distance. And since we are dealing with an attractive force, so our force will be expressed as minus k upon r square. And this force is a function of r. Here k is a constant. Now since we know our force, we can derive our potential energy. Since V can be derived from the integral of force. V is equal to minus integral of force with respect to dr. So we can obtain our potential energy as Vr equal to minus k by r. In our previous lectures, we have derived the equation of orbit. And the well-known equation of orbit is d2u upon d theta square plus u equals minus m upon L square u square multiplied by force, which is a function of 1 by u. Here what is u? 1 by u means r. Hence our force, which is a function of r, will be in terms of u. If we are going to express it, force will be function of 1 by u, which is equal to minus k upon r square. That means this is minus ku square. So we have equation of orbit as d2u upon d theta square plus u. This is equal to minus m upon L square u square, putting the value of force, which is minus ku square. I get my equation as d2u upon d theta square plus u, which to be equal to mk upon L square. Here I am writing the factor u minus mk upon L square to be y. Now I am writing the expression on the equation of orbit, which was in the form of u. I am changing my variable from u to y. So in order to change this, I have to find the second derivative. That means I will get d2y upon d theta square, which will be equal to d2u upon d theta square. So using second and third expression, in first I get d2y upon d theta square plus y equal to 0. This is second order differential equation. And we are well familiar with the solution of second order differential expression, which can be expressed in the form of cos function. Hence the general solution of this equation will be y equal to u dash cos theta minus theta dash. Now I can find the value of u. Since u is y plus mk upon L square. So I can obtain my u, and using this u, I will find the value of r. U will be equal to mk upon L square plus u dash cos theta minus theta dash. Since u is equal to 1 by r, I get it to be equal to mk upon L square plus u dash cos theta minus theta dash. Here u dash and theta dash factor are constant factors, and for simplicity I am choosing the factor theta dash to be 0. So I get 1 upon r, which is u, to be equal to mk upon L square plus u dash cos theta. I get my value of r as L square upon mk divided by 1 plus u dash L square upon mk cos theta. This equation represents a conic section. Hence, we have derived the Kepler first law of planetary motion. According to the Kepler first law of planetary motion, orbits move around orbits move by taking a path forming a conic section. Orbits are conic section with the center of force at the one of foci. Now, we will define this conic section as a curve, which I am showing you. I am taking this to be a conic section. This is defined as a curve for which distance from a fixed point, this is my fixed point, to a fixed line, and the ratio of these two distances is constant. Assuming the distance of this curve from a fixed point, which I have denoted as focus and taken as distance r, and the distance of the curve from a fixed line is denoted by small d. This fixed line is termed as directrix. So the ratio of these two distances, that means distance r and distance d, the ratio r by d will be constant, and we have denoted this constant by epsilon. And this constant epsilon is termed as eccentricity. Here we have taken the distance between focus and the fixed line, which is directrix, to be capital P. So this distance, focus, which is a point, and line, the distance is capital P. We can find the distance from the figure assuming this angle to be theta. The component of r along x-axis will be r cos theta. So total distance capital P can be expressed as d small d plus r cos theta. The value of small d will be equal to r upon epsilon plus r cos theta. Now, in order to simplify our expression, I am defining another parameter, which is small p. This small p can be expressed as epsilon capital P. Epsilon we have already discussed is eccentricity. So from here I can get capital P to be equal to small p upon epsilon. So substituting the value of capital P as small p upon epsilon, which is equal to r upon epsilon plus r cos theta, small p comes out to be r plus r epsilon cos theta. From here I can get the value of r as p upon 1 plus epsilon cos theta. This value of r is obtained from the definition of conic section, and we have also find the value of r using equation of orbit. This also represents a conic section, so we can compare the equation of conic section, one expressed by equation 5 and other which has been expressed as equation 6. So comparing these two, I get the value of small p as L square upon mk, and my eccentricity is found to be equal to u dash L square upon mk. So we have derived our Kepler first law, according to which orbits follow a conic section. Now in our next lecture we will define that in which condition the conic section will take a shape of parabola, or we can say our orbit will be either parabolic, hyperbolic, and under which condition it will be in elliptical nature. Thanks a lot for watching.